Welcome everyone. Today we'll discuss the problems related with the preparation of acetate and phosphate buffer. So let's start with the problems first. Now if you'll see the first question, in this particular question, it has been asked what are the concentrations of acetic acid which they have represented in the form of HOAC and its conjugate base, that means the acetate, in a 0.2 molar acetate buffer. They have given the pH value of 5 and the Ka of the acetic acid they have given 1.70 into 10 raised to the power minus 5. We can solve the same question in 3 different ways, and let's have a look on all the 3 different ways where we can solve this problem. Now the first thing, what are the things they have mentioned in this question? Now a couple of things you need to remember. When you are talking about the acetate buffer, that means it is going to be composed of acetic acid, which you can also represent in the form of HOAC, which is a weak acid. And then we have to consider its conjugate base, which is going to be CS3CO minus, which you can also represent in the form of OAC minus, which is a conjugate base. Remember, when I'm saying 0.2 molar acetate buffer, that means this 0.2 molar acetate buffer is going to consist of CS3COH as well as CS3CO minus. I need to find out the concentrations of these two components at a pH of 5. We all know that acetic acid is a weak acid. In water, it's going to ionize slowly to form acetate, and the released proton will combine with water to form hydronium ion. Now, what is the Ka acid dissociation constant value going to be for this equation? The Ka is going to be concentration of acetate and then the concentration of H3O plus divided by concentration of acetic acid. I'm neglecting the concentration of water because the concentration of water is not going to change much. We have seen these concepts in our previous lectures. Now the value of K is given. The value of K is given, which is 1.7 into 10 raised to the power minus 5. What is the concentration of CS3CO minus going to be? Now remember, the concentration of CS3CO minus will depend upon how much protons are getting released from this acetic acid. So we can consider at the initial time point, the concentration for this acetic acid was 0.2 molar. I'm not bothered about the water, and the initial concentrations of acetate and hydronium ion are going to be 0. With time, with progression of the time, this acetic acid is going to going to release proton, and let's assume that the amount of proton which this acetic acid is going to release is X, and depending upon that, the X is going to be the concentration of CS3CO minus. Remember, this CS3CO minus is coming from the proton which is released by the acetic acid, which then combines with the water to form hydronium ion as well as CH3CO minus. So acetic acid is releasing H plus, which combines with water to form H3O plus, and CH3COOH itself forms the conjugate base CH3CO minus. H3O plus, the the pH for this solution is given, it's 5. So if 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 the pH is 5, I can write it here. If the pH is 5, simple. What is the concentration of hydronium ion is going to be? We all know that pH is equal to negative log of hydronium ion concentration. So if 5 is given, I can take the anti-log value, and if we'll try to solve it with the help of the calculator, we are going to get the concentration of hydronium ion equal to 1 into 10 raised to the power of minus 5 molar. So if we'll focus here, CH3COH, I can keep the value as X as discussed in the previous equation. H3O from the question, we can figure it out, and it's 1 into 10 raised to the power minus 5. What is the concentration of CH3COH is going to be at the final equilibrium? So it's going to be, initially it was 0.2, it is going to dissociate some, release some proton. So I can write it as 0.2 minus X. Simple equation, just try to solve it, and you will get 3.4 into, I have solved it, 3.4 into 10 raised to the power minus 6 equal to, I also need to consider this X term on the left hand side. So it's going to be minus 1.7 into 10 raised to the power minus 5 equal to, I'm just solving this equation, equal to 1 into 10 raised to the power minus 5 X. So let me check it once more. I have multiplied these terms, 3.4 into 10 raised to the power minus 6 minus 1.7 into 10 raised to the power minus 5x, and then on the right hand side 1 into 10 raised to the power minus 5x. So you can rewrite this equation as 3.4 into 10 raised to the minus 6 equal to 1 into 10 raised to the power minus 5x plus 1.7 into 10 raised to the minus 5x. So what is the value you are going to get? You just add it. So let me move to the next slide. 3.4 into 10 raised to the power minus 6 equal to, I can rewrite the term on the right hand side as 1 plus 1.7, 2.7 into 10 raised to the power minus 5x. I can solve it for x with the help of a simple calculator, or you can take your own time, and you will get x equal to 0.126, and we all know that X is the concentration of conjugate base, which in this case is CH3CO minus. Now for the concentration of CH3COH, what I need to do, I need to subtract this value with a 0.2. So 0.2 minus 0.126, and you will get the exact value as 0.074 molar. So what are the concentrations of CH3COH and CH3CO minus we have got? For CH3COH, which is a weak acid, it's 0.074 molar. And for the CH3COO minus, which is a conjugate base, we are getting 0.126. Just try to add up these values, and what you will find, that it's going to be, if you add these two terms, the concentrations, if the final value you are going to get is zero point 0.2 molar. And that's what we have started from the question, that I want to prepare zero point 0.2 molar acetate buffer, and I want to know the concentration of acetic acid and acetate ions. So these are the values which will get. Sorry, this is for the acetate, and this is for the acetic acid. Now let's have a look, the second way in which we can solve this equation. Go back, read the question very carefully, and you will find out that we are talking about the buffer. And it's a buffer of a weak acid and its conjugate base. So one can use the famous Henderson-Hasselbalch equation, which is equal to, where we can write the term pH equal to pKa plus log conjugate base, concentration of conjugate base, and the concentration of acid. Many of the values are given. The pH in this question is given 5, pKa is given, not directly. The K is given 1.7 into 10 raised to the power minus 5, and you can just try to calculate the pK by pK equal to negative log K, and you will get a value close to 4.769, and you can round off this value to 4.77. Perfect. So the pH is given, pKa is given, the log concentration of conjugate base. Just now we have seen that the concentration of conjugate base from this chemical reaction, I can consider this as a X, and the concentration of acid, what that is going to be 0.2 minus X. Simple. Solve this equation. 5 minus 4.77, which we are going to get it as 0.23 equal to log X 0.2 minus X. I can take antilog of 0.23 and we'll get the value as I'm trying to calculate the value, and we'll get as 1.698, where we can round off those values and can consider 1.70. So this value is the antilog of 0.23. Remember, it's a basic log equation, so I can solve the concentration of X divided by concentration of 0.2 minus X equal to 1.70. Try to calculate it for X. It's a simple equation, and the values of X you will get same, 0.126. Just try to solve it with the help of your calculator, or you can try it on your notebook, and you'll get X equal to 0.126. That was the same value I was getting it from the method 1. So let's consider it as a one way to solve this problem. So X is coming out to be 0.126 here again, which we all know that X is the conjugate base. And so I'm writing it as Cb, which corresponds to conjugate base. And the concentration of acid is going to be 0.2 minus X, which is going to be 0.074 molar. Perfect. So these are the values I'm getting. These values are the same. That's what I said at the start of this question, that I can solve the same question in 3 different ways. So this is the second way. And the third is going to be a very simple way, where you can still use this Henderson-Hasselbalch equation, pH equal to pK plus log conjugate base. Remember, in this question, the conjugate base is CH3CO minus, and then the concentration of acid. We'll simplify the equation. pH, I can keep it as 5, which is given in the question. pK, just now we have seen, it's coming out to be 4.77 log. I will just calculate the ratio. I will not put the value. So I will just calculate the ratio of the concentration of conjugate base and acid. And what we will find out that when we will calculate the ratio of the concentration of conjugate base and acids, it's coming out to be 1 point. Just now we have seen it's coming out to be 1.70 equal to concentration of conjugate base and concentration of acid. Now I can rewrite this equation as in a different way, and we'll see. So we all know that the concentration of conjugate base plus concentration of acid is going to be how much? I'm just adding these two things, and we have seen it from the question. It's going to be 0.2 molar. That's what I said at the start of this question, that this acetate buffer is going to consist of acetic acid and acetate. So I can rewrite this equation as 0.2, where the concentration of conjugate base can be considered as 0.2 minus concentration of acid. So simple. Put these values in this equation, and we'll get the right answer. So 1.7. Just now I have seen conjugate base. The concentration of conjugate base I can rewrite as 0.2 minus concentration of acid. Remember, these brackets represents the concentration term. Let's consider the concentration of acid is X. So I'm going to get 1.7 equal to concentration of conjugate base, which is going to be 0.2 minus X. How about the concentration of acid? I have considered the concentration of acid to be X. Simple. Try to solve it, and we'll get 1.7 X equal to 0.2 minus X. Remember, it's going to be 2.7 X equal to 0.2. So X is going to be 0.074 molar, which corresponds to concentration of acetic acid. That's what we have considered. That's what we have considered as the X, which is, this value is going to be the same whatever we got in the previous solutions, 0.074 in the second approach. Remember, even in the first way of solving this problem, we got the concentration of acetic acid is 0.074. That's what I'm saying it from the start, that you can solve the same question in three different manner, and then I have to calculate the concentration of conjugate base, which is going to be 0.2 minus X. That means 0.2 minus 0.074, which is going to be equal to 0.126 molar. So, all right, it seems all right to me. In all these three different approaches, we have got the concentration of conjugate base as 0.126 molar, and the concentration of acid as 0.074 molar. Coming back to my questions, they have asked what are the concentration of acetic acid and acetate in a 0.2 molar acetate buffer, and these were the values which were given. So you can opt for any of these methods. All of these are absolutely right. You can even come up with your own way of solutions and can comment in the comment box. Now coming back to the another question, it's given It's related to the phosphate buffer. So we have discussed about the acetate. Now we'll talk about the phosphate buffer. Remember, these buffers are very, very, very important when you are performing your research experiments in the lab. We do need to, for any kind of the practicals, if I'm working with the biomolecules, any kind of biomolecules, be it carbohydrates, lipids, proteins, or nucleic acids, I need to maintain a optimum conditions by dissolving my biomolecule it in a suitable buffer, and we keep on using such kind of a buffer. So we'll talk more about the buffers in our subsequent lectures. So coming back to the question, I have been provided with a stock solution of 1 molar KH2PO4, fine, and 1 molar K2HPO4. So remember, there are two different kinds of salts. Prepare 200 ml of 0.15 molar phosphate buffer. So I have to prepare 200 ml of 0.15 molar phosphate buffer with a pH of 7. All right, the pK is given. The pK is given again. So what I need to do, I need to consider some chemical reaction, and I can write that chemical reaction as H2PO4 minus. So remember, it's a potassium salt, so I can consider this as a H2PO4 minus, getting in an aqueous solution. What that is going to form, that is going to release a proton. It's a weak acid, so it's going to release proton very slowly with 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 a progression of time, and going to form HPO4 2 minus, and the released proton will combine with H2O to form H3O plus. So simple equation. So you just need to read the question very carefully. What are the given? So by looking at the question, I can tell you that it's a weak acid, and then it's a conjugate base. That's what we want for the preparation of a buffer. All right. So we'll write the equation, and the pK is given. So we all know that the K is, for this chemical reaction, is going to be HPO4 2 minus, and the concentration of H3O plus divided by the concentration of H2PO4 minus. I'm not bothered about the concentration of water. Why? Because the concentration of water is not going to change much. Okay, simple. Again, you can solve this question with different approaches. I will just use one. So I'll go ahead with the famous Henderson-Hasselbalch equation, which is widely used for solving such for solving problems related with the buffers. And just try to derive this equation. Very important. You should not memorize it, but try to derive it, and you'll realize that you can gather maximum number of information from this equation, so which is pH equal to pKa plus log conjugate base by concentration of acid. Now, what are the values which are given in this question? pH 7 given, perfect. pK, is it given, or do I need to calculate? No, they have given you the pK, so I can keep it as 7.2. How about the law? How about the concentration of conjugate base and concentration of acid? I will not put any x values. What I will do, I will simplify this equation by calculating the ratio of the concentration of conjugate base and the concentration of acid. So let me rewrite this equation. 7 minus 7.2, I'm going to get minus 0.2 equal to log concentration of conjugate base by concentration of conjugate acid. So just try to calculate the value. You can take antilog of minus 0.2, which is going to be 0.630, 0.6309, and I can consider the value as 0.631 equal to concentration of conjugate base and concentration of, it's a ratio, 0.631 is a ratio, remember. 0.631 is a ratio of concentration of conjugate base and acid. Same way, I will put some values here, but before that, remember, in the question it's given, it's a phosphate buffer, so the concentration of conjugate base and the acid is given how much? Go back to the question and read it. It's given 0.15 molar phosphate buffer. So remember, the 0.51 molar phosphate buffer is going to comprise of the conjugate base and its acid. Now I can write this equation as conjugate base equal to 0.15 molar minus concentration of acid. Let's assume the concentration of acid to be X and put these values in this equation. So 0.631 equal to concentration of conjugate base, which is 0.15 minus X divided by concentration of acid, which is X. Solve it for X, which you are going to get as 0.631 X equal to 0.15 minus X. So you will get 1.631 X equal to 0.15. Let me calculate the value of X. So we are going to get 0.091. So X is coming out to be 0.0919. I will consider that as a 0.092 molar. Perfect. So I got the value for the concentration of acid, which in this case is, what is my acid in this case? It is KH2PO4. I can write it as H2PO4 to H2PO4 minus. And its concentration is coming out to be 0.92 molar. Great. What is the concentration of conjugate base going to be? It's going to be 0.15 minus X. 0.15. I think I'm making one mistake. If we'll try to calculate this value, the X is not 0.92, but rather 0.092. So I've made a mistake here. So I have to rewrite it. 0.092. Just do it by yourself and you'll get this value. So X is nothing but 0.15 divided by 1.631, which corresponds to 0.091, and I have round of those values to 0.092. Perfect. So the concentration of conjugate base is going to be 0.15 minus 0.092 molar, which corresponds to 0.15 minus 0.092 equal to 0.058 molar. Good. Now, have I solved this question? No, because they have asked how to prepare this much ml of 0.15 molar phosphate buffer from these stock solutions. So I have to prepare 200 ml. I have calculated the concentration 0.092 and 0.058. Remember, molarity equal to gram moles of solute per liter of the solution. So I can rewrite molarity as moles per liter. Same here. But they have asked to prepare me 200 ml. So I can, what I can do, I can I can consider the volume 200 ml in this in this equation, and then can calculate the mole. So remember, simple, 0.092 molarity, moles of solute by volume of solution in liter, which is given as zero point 0.2. So how much moles I am going to get? 0.092 into zero point 0.2, which corresponds to 0.0184, 0.0184 moles. So 0.0184 moles for H2PO4 minus. Same way I have to calculate it for HPO4 2 minus. Remember, it's a dihydrogen phosphate. It's a monohydrogen phosphate. So what is the value I'm supposed to get it for HPO4 2 minus? It's going to be 0.058 into 0.2. I've changed the ml to the liters, and the values which I'm getting is 0.0116 moles for HPO4 2 minus. I haven't solved this question yet because what they have given, I need to prepare 200 ml, perfect, 0.15 molar phosphate, perfect, I have calculated, but this buffer, I have to prepare it from my stock solution, which is 1 molar KS2PO4 and 1 molar K2HPO4 given. So I have been provided with these stock solutions in the lab. So let me recalculate it. So they have given 1 molar K2HPO KH2PO4, and they have given me 1 molar K2HPO4. Remember, whenever you prepare your buffers, most of the times you keep stock solutions ready, and then with these stock solutions you prepare the buffer of your interest. So it's easy to do, so that you don't need to go back again to these calculations and keep on making these stock solutions, keep on making these keep on making these different kind of buffers with a different kind of values. So what people generally do, they prepare a stock solution, they can store it at either room temperature or 4 degrees Celsius, and then they dilute it to the buffer of their desired pH and desired concentration. Coming back, they have given 1 molar KH2PO4. That means it's the 1 mole is present in a liter, 1 liter. Same here, 1 molar K2HPO4 is present. The 1 mole of K2HPO4 is present in 1 liter. Now I need to go back. I need 0.0184 moles. That means for H2PO4 minus. So 1 mole is present in 1000 ml or 1 liter. So 0.0184 mole is going to be present in how much ml? So 0. Simple, 1 mole in, sorry, so 1 mole is present in, I need, I'm just changing the color of my pen. So 1 mole is there in 1000 ml. 0.0184 mole is going to be present in going to be present in how much ml? 0.0184 into 1000, which corresponds to simple 18.4 ml, because these are the simple ways to represent your volume, or you can call it as 0.0184 liters. So I need 18.4 ml of KH2PO4, which is there in the lab as a stock solution prepared by either the any lab assistant, or you can still prepare by your own. And then I need 0.0116 HPO4 2 minus 0.0116 mole HPO4 2 minus. That means, which corresponds to either this much liter or 11.6 ml. So I need to summarize it. What I need to do, I need to take 18.4 ml of KH2PO4 solution. So I need to take 18.4 ml of, rather 1 molar KH2PO4 solution. I need to take its conjugate base, which is going to be 11.6 ml of 1 molar HPO4 2 minus, or you can call it as K2HPO4. I need to raise up the volume. I need to raise up the volume finally to 200 ml with the help of double distilled water or autoclaved water. Why? Because remember, they have asked me to prepare the 200 ml. So if we'll add these two volumes, which corresponds to close to 130 ml, so it's 30 ml, and the remaining 170 ml I need to raise the volume with the help of double distilled water or the autoclaved water. I hope these solutions are clear to each and every one of you. If not, please feel free to comment and let me know if you have any extra questions related to the buffer, or do you have any other alternative approach which you think you are right. You can write it in the comment box. Thanks everyone.